My name is Sebastian Rodriguez, and this is my Physics 2212 Lab 5 report. In this lab, we will be measuring the time it takes for a magnet to fall across the length of a tube of aluminum foil. We will examine the interaction between the changing magnetic field that is produced by the falling magnet and the induced current, which will produce a magnetic force that counteracts the motion of the magnet. To do this, we will be using Faraday's law to relate the time-varying magnetic field to a non-Coulomb electric field in order to derive the EMF which drives the current in a loop. And by doing so, we will be making a computational model, which we will compare to the real-life model. So the main result of this lab is comparing the time that it took for the magnet in the real experiment to fall across the entire length of the tube, which was 1 second, to the time that it took the glow script model, the time that it predicted, which was 0.965 seconds. Here are some of the important formulas that we're going to be using today, which are Faraday's law, which relates the EMF to the closed loop derivative or closed loop integral of the non-Coulomb electric field, and the time varying magnetic field, which we use by deriving the magnetic flux. Next is the Biot-Savart law, which gives us the magnetic field, as well as the Lorentz force, which gives us the force. So here are some assumptions that we're going to be making for our model. And for the computational model, we're going to be assuming that the tube is a stack of infinitesimally thin rings that each produce a small component of the magnetic force on the magnet, which we then add up to get the total force acting on the magnet at any given moment. We'll also assume that there are no external magnetic fields and that the air resistance is negligible. For the checkpoint questions, we can't use the Ferris tube because it contains iron, which has magnetic properties, and this would mess up and skew our data. And what happens to the magnet is that the magnetic force created by the induced current opposes the magnet's motion, which then slows the magnet. And this means that it goes slower than it would if there was nothing acting on it besides gravity. Those previously explained conditions, we perform the experiment. The materials are a 35 centimeter tall tube of aluminum foil that has a thickness of 0.8 centimeters of foil on it, and a bar magnet with the mass shown right there and a moment of 6.57. And we're also going to use a timer to determine the time it takes. So we put the magnet at the top of the tube, drop it, measure how long it took to travel the whole distance. We did this 5 times and then averaged it to get an average of 1 second for the magnet to drop. Now that we have that data, we can make the computational model to compare that real data to what the code is going to say. So here I just set some initial conditions and I created the bar magnet here as well as a function to calculate the magnetic field of the bar magnet, which was code that we created for Lab 3. This part, I created a function to calculate the magnetic flux from each ring due to the falling magnet. And this is going to be really useful. We'll see in the next slide what this produces, as well as there was also like the pre-made function to like actually create the tube and the magnet and everything, which we'll see in the next slide. Okay, so here on the left you can see the actual model that we created with the blue and red ring. And at the top you'll see the velocity versus time graph, and we'll get to that later. Okay, so in this model, the red color represents the counterclockwise current, which produces a force upwards. We can tell this by the right-hand rule. If you curl your fingers in the counterclockwise direction, your thumb will point up, indicating that's where the force is. And it's the opposite for the blue one, which is the clockwise current, and that one produces a force downward. If the magnet was flipped, nothing would change except for the direction of the current in the tube. The time would still be the same and everything. This model was actually really close to the real world model. The time that it took, as you can see in the graph, was 0.965 seconds, meaning that the difference between this computational model and the real world model was only 0.035 seconds. This velocity graph shows that initially gravity overpowers the magnetic force, then the magnet overpowers gravity, but eventually they balance out. If the resistivity of the conductor was reduced to zero, then the induced current would be much greater, and the force that's acting on the magnet would be greatly increased, meaning that it would move super slowly or just stop moving altogether. If there were holes or slots cut into the tube, the current induced would be less, and the magnetic field would be less, so it would fall faster.